Hey everyone! Thanks for joining us for the next session of AI Apps and Agent Dev Days. My name is Anna. I'll be your producer for this session. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'll turn it over to our speakers for today. Thanks so much for joining.
Hi, everybody.
Hey, everyone.
Hi, my name is Anthony Shaw. I'm from Microsoft, and with me today is Stephen from NVIDIA. Stephen, do you want to introduce yourself?
Absolutely. So my name is Stephen McCullough, and I am an AI solutions architect with NVIDIA. So this means that I get to work with Microsoft on implementing all of the latest and greatest AI technology into Azure. So a bit about the program. Microsoft and NVIDIA have been working in close partnership and continue to work in close partnership in order to power the next generation of AI and machine learning. They're doing this through the deep integration of NVIDIA's accelerated computing platforms, along with Microsoft Azure's global cloud infrastructure. So this webinar series is it's a big part of that. We really want to show users like you how to best leverage all of this magic and innovation going on between Azure and NVIDIA. So make sure to tune in to the series as we explore these integrations and show you how to best apply them in the real world.
Great, thanks, Stephen. Yeah, my name is Anthony. I work for Microsoft. I'm joining here from Redmond, Washington as well. I'm visiting for the week, so yeah, it's been an adventure. Yeah, I'm really excited to kind of go through some topics with you today, talking about AI performance. So let's get stuck in. So what we want to cover with you today, this is a pretty deep technical talk, so we will be going into some details on the performance of the models, as well as the engines that kind of drive what we call the inferencing cycle for AI. So we're going to be getting into some deep technical detail, looking under the hood. But first of all, I'm going to talk about sort of high level, what is AI performance and what does it mean to a user. Then we're going to kind of dive into the details. We're going to look at benchmarking in particular, and like with a couple of different approaches to benchmarking at a lower level and again at a higher level. And then what things you can do to accelerate performance, and then what's kind of on the bleeding edge of techniques that you can apply in your AI inferencing to improve performance. And Stephen's going to share some stuff coming out of NVIDIA Labs that's been really exciting and what that means for AI apps and performance. The next slide. So yeah, first off, when we talk about performance, there is, I guess that as a term, if you talk about application performance or network performance, generally we're talking about speed. With AI, we can be talking about a few different things. The performance can be, well, how well does that model perform? So how accurate is it? How well can it respond to questions? How well can it keep on topic? How well can it retrieve information from a large body of text? Or for a reasoning model, how well can it reason over a problem and give you an accurate answer? So these are all kind of different metrics we can look at with AI models. What we're talking about today is the speed. So that when we talk about performance, we're talking about speed today. So we're going to be talking about the serving performance, which is really looking at two kind of key points. With the key metrics are latency, which we'll explain, and the throughput. And these are the two things we want to talk about. So let's kind of bring that up to what does it mean for the user in the next slide. So the way we measure this is kind of dependent on the use case. There are lots of different types of AI models. There's large language models, there's VLMs, embedding models, which are used often in RAG. There's re-ranking models, which are used again in RAG and search algorithms. We've also got world generation models. So generally, when we talk about AI models today, people kind of think about LLMs, but in sort of modern agentic AI applications, we've often got more than one model at play. But most of the engines that we use to actually run the AI models are quite similar. So the actual kind of core component, which is the inferencing engine, is based on the same technology. So whether it's producing text in tokens, whether it's producing embeddings or vectors for embedding models, or whether it's re-ranking things within the algorithm, these are kind of built upon the same foundation, same architecture. And then the application is what we put on top of those AI models. So whether we're generating text with LLMs, whether we're generating images with an image model like DALL-E, or video generation using one of the text to video models. The way we think of the models is we have an input type, which could be text, so you ask it a question, and then we have an output type, which it could be text or image or video. So you've also got types of models where you give it video and it gives you back a text description. So we kind of think about the input and output of the different types of models and how they work. We've also got coding models and agentic models. But like I said here, even through all of these different types of models and the different modalities of the models, so what you put in and what you get out, the kind of fundamentals of the actual performance are more or less the same. So the stuff we're going to talk to you about today would apply to everything in this category. Next slide. Cool. So how do we plan for performance? I think this kind of comes back to user expectations. And, you know, as you're somewhat, everybody on here is someone who uses computer systems, whether they're their mobile phone or their desktop computer, or they're using any kind of electronic device. You have an expectation as a user that it responds within a certain time frame. So if I open an app on my phone or I click on something on my desktop, my expectation is that that actually happens within about 10 to 100 milliseconds. If it takes longer than that, so if I open an app or press a button on my phone and it takes longer than 100 milliseconds, it feels slow, because we intuitively have this expectation that because the device is in front of me and it's running on the computer, it should respond near instantly or very, very quickly. So when people say that they feel like their device is running slowly, that you know, often it's because their expectations are set based on what they've experienced before, and then if you drag that out, then it feels slow. Whereas if I was sending something over the network, or I'm loading a website or watching a video or something online, then my expectations are different. You know, I wouldn't expect that when I start something on Netflix, it responds within 50 milliseconds. I'm quite happy for it to take half a second for a second to start playing. And that's because my expectations are different, because I know that I'm using something on the network. Now, even though AI is a really new thing that we're doing, especially text generation, it's quite new that users are using AI. You know, we've had AI for 20 years, but it's mostly been used for like training and things like that in the background. It's quite a new idea that users are actually interacting with it directly. And so where we think the expectations are right now is that users are aware that AI can take 1 second, several seconds, or even longer to respond. So users' expectations are set that way. Next slide. So the reason I bring this up is because when you're introducing AI into your application, you want to align that with the user's expectations. So if you had something like in your app right now, you've got a search feature, and if the user types in a question and clicks search, their expectation is that that's going to be fairly quick, because normally keyword search in a database is a pretty fast operation. And then if you build that out, so if you introduced an LLM to every single search query, and you didn't make it clear, or you just added that feature in, all of a sudden something which took 100 milliseconds now takes a second, 5 seconds. The user's expectation is that the feature is suddenly slower than it was before. And this is what I think is really important, is that we need to think about AI performance, because if we're putting AI into features in our applications, we need to kind of align that with the expectations of the user. The next slide. When that's actually completely fine is when the users ask the AI to go and do something which would otherwise take them several weeks, like I want you to do a deep research into a particular topic, you know, study 20 different papers, write me a summary of what you found, or look into a particular topic and survey like 100 websites online. So if the AI was doing some work like that, my expectations as a user was, well, that would take me 2 weeks to do. I'm perfectly happy with AI doing that for an hour or 2 hours. That seems fine. The difference is that you start it on the task and it would come back to you when it's finished. So next slide. So in the top right-hand corner, there's a QR code to something called the HAX framework. This is the Human AI Exchange. It's kind of like our kind of user experience guidelines that we developed here at Microsoft for building sort of human and AI experiences. So where you're adding AI to your applications, then what kind of things should you consider? And to kind of summarize some of those, which I think is really important, especially with the context of performance and what I've talked about already, is if you're putting AI into a feature that was previously really fast, you've basically added a half a second, or sometimes even more latency to that feature. So you really need to keep that in mind. So how do you kind of build a user experience so that the user's expectations for clicking on a button, typing in a search box is aligned with how long it's actually going to take to do that? The AI continues to get faster and faster, and we'll probably see over time that we'll bring that down from a few seconds as it is today. Sometimes it's only half a second, and we'll probably continue to bring that down over time. But right here, right now, the infrastructure that we have and the size of the models and the complexity of them, which we'll talk about, means that it does take quite a bit of time to calculate the answers. The other thing is that when you have this feature, you should always use streaming. So when the user interacts with AI, you should always start streaming back the answer directly to the user. So don't wait for the entire result to populate. I also strongly recommend not using reasoning models, which is a type of language model, unless you really, really need reasoning, because they generally take a lot longer to run, because they're doing reasoning before they start streaming back the answers to you. And definitely do use AI to enrich features. There's a lot of capabilities that we can explore. Have the option to disable or dismiss the AI features. This is part of our usability guidelines. Always stream back results, as I said. And if you think something is going to take several minutes or even several hours for the AI to do, sometimes we have agentic workloads which can take several hours because they're doing huge amounts of work reviewing, hundreds of documents and looking at websites and things like that. So it's perfectly fine to have the option to notify the user later. Next slide. So yeah, we're now going to look under the hood and get into some details.
Yeah. All right. So when we're talking about AI performance, we're going to go into some depth here about what's really going on under the hood and establish some really important concepts that will, form the foundation of your understanding. So these topics around how we can improve performance will make a lot more sense. So whenever we talk about LLMs and how they generate content, generate tokens, really the LLM is just generating a single token at a time. And for every token that it generates, the LLM needs to examine every single token that has come before it. It takes all of these tokens that have come before the one that it's processing, and it computes the positional embeddings and the attention for each of these tokens, passes those values through its neural network, and then the LLM will choose that single next best token. And once that's done, you have to do the entire thing over again. So, you can see here, if the prompt is make me sound smart, the first token that it generates is LLM. But in order to just generate this one single token, the LLM had to embed all of the existing tokens that were in the prompt, pass them through its model weights, and then calculate what's called the K and V values for each of these tokens. And this is really important because this is going to be used throughout the entire generation process. So remember, for every single token, we have to do this entire process over again. So if the next word is LLM training, if that's the next token, then we have to examine make me sound smart LLM, and pass all of that through the entire neural network again, compute the key and value matrices, and then the LLM will say, the next best token is the word training. And so then you just completely reiterate that process for every token. So an important thing to note here is that these key and value matrices, they don't change for each token. So whenever you calculate let's say we submit a prompt, make me sound smart, and it's generating the key and value matrices for all of these tokens. These key and values for each token aren't going to change throughout the entire generation process, the entire inference process. So we really need to only generate them a single time. And this is really important to know because what pretty much every single AI model does is they cache these key and value matrices in what's called the KV cache. So this is a fundamental concept to be very familiar with whenever we're talking about LLM inference. So again, we pass make me sound smart LLM, the new token we just generated, back through the LLM, and it tells us to generate the word inference. So we were able to save a lot of computation with this because we didn't have to recompute these key and value matrices for all of these existing tokens. We did have to calculate the key and value vectors for this new token, but that's only one token compared to all of the existing ones. So this KV cache is a huge boost to performance, and pretty much every single AI model works using this. So whenever it's generating tokens and whenever it's processing the initial prompt, these are two different processes. And really, these two processes make up the entire inference cycle. The first of these processes is called the prefill phase. And during prefill, that's where you are calculating the key and value matrices just on the prompt that you gave to the LLM. This isn't calculating any key and value vectors for any newly generated tokens, just the prompt that you gave. And it ends whenever the LLM generates the first output token. So if you think about yourself submitting a prompt to an LLM, and you might have to wait, let's say, half a second or a second for it to come back with just that first token, this is exactly what is going on in that time. This latency that you're seeing is caused by this prefill process. It's caused by this key and value matrix generation based off of the prompt you provided. So if we want to cut down on the latency and make that model start responding more quickly, we want to optimize our prefill process. And there's some of the brightest minds in the world working on exactly this. So we see significant decreases year over year, but you might still feel that latency whenever you use an LLM. Now, the second major portion of the inference cycle is called the decode process. So after the prefill is done, the initial KV cache is generated. The decode refers to the part of the process where each individual token is generated. And in this process, remember that each generated token gets passed through the LLM again for every preceding token after it. So remember, if I say make me sound smart, and then make me sound smart LLM, whenever I want to generate the token after LLM, that generated token that is LLM goes back through the neural network. So whenever we are using an LLM, and you might say like, wow, it's generating just like a sheet or an essay of maybe 1,000 tokens in just a couple seconds, that is the throughput of the model. We measure that in tokens per second. So whenever we want to optimize our throughput and we want to generate more tokens per second, that's when we want to optimize our decode. Again, this is a huge topic of research for tons of AI engineers out there, and we see numbers increase over time. And we're going to talk to you more about how we can improve this throughput and decrease the latency with a couple different techniques. So whenever you are running inference on your LLM, it's most likely not just processing your prompt at any given moment. Your LLM is likely using something called batching to process multiple different prompts, multiple requests, all at the same time. And the reason it does this is because it makes much better utilization of your hardware. If you have, an NVIDIA GPU and you're just running one prompt at a time, all in series, you're going to be wasting a lot of, potential throughput from your model, and especially when you are running large-scale deployments where you might have hundreds of users or even thousands of users. Batching becomes a really important part of this process. And it's not like batching is some, magic cure to where you can just increase your batch size and process 1,000 prompts at any given moment. There are limits, and, rule of thumb is that when your batch size starts to get a bit too big, you'll start to see increased latency. But this is an important topic to understand as we go throughout this presentation, because it is so vital to how LLMs work. All right, so we're talking about LLM performance and what's behind the scenes, but we also need to understand how we can measure this. How do we understand and benchmark and track how performant our LLMs are? And that comes down to benchmarks. And now, as Anthony mentioned at the beginning of the presentation, there are benchmarks and performance metrics out there for all sorts of things regarding AI models, like humanities last exam, or the AMER 25 math exam. These are more so geared towards the accuracy and intelligence of the model. But what we're looking at today is a lot more applicable to the model users and model owners, anyone who runs, ML ops or DevOps. If you're in that field, this will be very applicable. If you are training a model and you are gathering your data sets and evaluating it, that's where you might use things like humanities last exam or some other intelligence benchmarks. So whenever we are thinking about, benchmarking performance, there's a couple different areas that we can use that we can benchmark at. So starting off at the lower level, we have we can start benchmarking the actual LLM engine itself using TRT LLM bench. Now, TRT LLM, that's Tensor RT LLM. It's from NVIDIA, and it's lots of tools combined under this umbrella. But TRT LLM is an inference engine that is really optimized for NVIDIA hardware. And TRT LLM Bench is a great benchmark to get really, really in-depth insights on how your LLM is performing. So you can get very low level into what the LLM is doing and how well it's doing it using TRT LLM Bench. So if you move a bit higher up the stack, you can actually measure the performance of the LLM endpoint itself. So when you start running your LLM model, it's if you're using TRT LLM or VLLM or SGLang, it's going to create an endpoint that anyone can send a request to. So a lot of tools out there exist, and a lot of tools out there are focused on measuring the performance of this endpoint. So for example, GenAI Perf from NVIDIA or SGLang's bench serving tool. These are both focused on measuring the performance, so the throughput and the latency of these endpoints. And this is really great because of the flexibility of these tools. You can measure an LLM that's running locally. You can measure an LLM running on Azure. You can measure a hosted LLM from a model provider. You can really get very creative and very flexible with what you're measuring and who's hosting it. And then what we want to look at as well with any LLM application is the performance of the application as a whole. So this is where Azure load testing really, really shines. We can get tons of different performance metrics about the entire application from just a single pane of glass. So Anthony will show us that in a bit, and it is very awesome, very helpful. So whenever you are benchmarking, essentially, whether you're benchmarking at the low level using TRT LLM Bench or you're benchmarking an endpoint, what's really going on is your benchmarking tool is sending like tons of requests to this endpoint or to your model and measuring the performance that it sees back. And the prompts that you are using, i.e. the data set that you're using, is very, very important here. Because if let's say you have an LLM running at your company, and this LLM is expected to receive a lot of code input, you want to make sure that you're benchmarking with code in that case. And to generalize that, you want to make sure that your data set just matches your real world data to the best of your ability. So there's a couple things to keep in mind there. Number one, the data types, whether that's going to be text or code or images or video, you want to make sure that you're benchmarking with that same kind of data type. Then you have your sequence lengths. So your input sequence lengths and your output sequence lengths are really important. And you want to make sure that your input sequence length is pretty much how many tokens are in your input or your prompt. And this does affect the performance of your model. So trying to, at least get an average of your user's input sequence length is really helpful. So when you benchmark, you can kind of mimic that really well. And a couple different things to keep in mind here. So I had a couple things to show as far as actually benchmarking a model. So right now, I actually have an LLM running on my Azure VM. This is a standard NC40 VM. So it has a single NVIDIA H100 GPU on it. So I'm just running a model locally on here. And I'm using it, TRT LLM, to serve the model. And I'll show you how you can actually benchmark this model. So I'll just run a quick health check. So I asked it, hello, please tell me a joke about the sun and moon. Let's see. Why did the sun and moon go to the party together? Because they were celestial beings. But in all seriousness, here's a Classic sun and moon joke for you. Why did the moon visit the sun one day? To see how the other half shines. I hope you enjoyed that. So it's very humorous, I guess, very clever, this model. So this is a Mistral 7B v0.1 instruct model, if you're curious. And so if you saw just how quickly it generated all these tokens, there's probably, just rough guess, maybe 50, 60 tokens in here, and it generated that in less than a second. So it's pretty incredible the kind of performance that we can get off of this system. All right, so now we know that the model is up and running well. Let's run Gen AI Perf to actually get some idea about how well the model's running. Ooh. Let's see. Oh, I am not running off of much sleep here. So what it's doing here is it is sending 8, or a concurrency of 8, which means like 8 simultaneous requests, and it's sending 40 of them. So we can think of like 8 kind of batches of 5 requests, 5 batches of 8 requests. And we configured the input sequence length, which is like, again, how many tokens are in your prompt, to be 3,200. We configured it to stop generating tokens at 800, and then a couple other things about configuration. So let's see the performance that it came back with. So the end-to-end latency, remember, this isn't, in this case, this is not the how long it takes to generate that first token, but this is how long it takes to complete that entire request. So on average, it was completing one of those batches of 8 prompts in about 4 seconds. And it was generating tokens at about 750 tokens per second. So this is just, in my opinion, like absurd performance. This is crazy. Generating 750 tokens per second. It's just mind-blowing. So, you'd be able to serve multiple users, multiple simultaneous prompts, all at the same time, using something like this. So this is a great way to measure your performance, sort of at the lower level, just isolating the model itself, getting some idea about how well it's performing. Now I'm going to hand it over to Anthony, who's going to show us more about benchmarking our AI application and focusing sort of in a more broad application scope. Oh, Anthony, you're on mute.
That was my fault. Sorry. Yeah, if we can share my screen, please, Anna. Can we see that now? Okay, great. Thanks, Stephen. So the thing I wanted to focus on next was how do we do a test, I guess, at the other end of the scale. So Stephen's showing like a lower level performance test, which is actually looking at the tokens coming out of the model, and you're running that test as close as you can to the model itself. And I wanted to look at a different type of test, which is a load test that we can run on the application, and then understanding what role the AI has in that performance. So what I've done is I've used a tool called Locust. Locust is an open source framework for Python. It's ideal for writing load tests, especially for web apps. And what I tend to do with chat tests is I'll generate a set of test inputs with the sort of starter questions for the conversation that the user would be doing. And in my case, my app actually has some tools that it would invoke. These particular tools, I think, are local tools, but if they were MCP or something like that, it doesn't really make much of a difference. And then I kind of vary the questions. I generated a few of these questions myself, and then I asked AI to kind of generate another 50 or 60 questions. So I kind of got a nice varied test base. And then what I've done in Locust is made a test user, And what we do with the test user, first of all, they have to log in. That's specific to our application. But generally, like you would need to log into an app before you're able to access one of the features. And then I've mimicked the user making a chat request. In this case, I'm using a framework from OpenAI called ChatKit. That's like the UI framework. But if you've got your own kind of layer or you've got your own API to initiate chat requests, you would put that in here. And what you do is you basically code the steps in Python. And what we do is we take this test, which is our locus test, and then we can drop that into Azure load testing. So Azure load testing is a place where you can upload locus tests. I can actually run that locus test locally on my machine. That's completely fine. In this particular case, I actually run this test on a schedule every 24 hours. And so it's basically running all week, which is why I wanted to offload it onto a service. So one thing we get with Azure load testing is we can basically get Azure load testing to run the test for us. So it generates all the traffic. So in this case, it's done 34,000 chat requests to my endpoint. And then I can basically log in and see I think it ran the test, this particular test over 18 hours, I think it was. So I can see what was the response time of the different parts of the test. So I've got like a login and a log out, which is nice and quick. But I've also got the chat request, which is like I can see here, like on average takes a second or a second and a half. Now that kind of tells me, okay, what's my expectation from the average response time? So I can see that here. But I actually want to dig into a bit more details. And because in this application I've got open telemetry, then I'm capturing all of that trace data whilst I'm running my test. And I can see that in application insights. And in Azure, what I would see during the load test is I'd see in the performance page in application insights, I'd see like the average times for the tests. This is all open again. Open telemetry is an open standard, and I'm using open source tools to actually trace the application. It's just that I have so much volume. I just want to see that at a kind of a high level and then drill into the details. So what you see with open telemetry traces is, okay, I had all these requests to my chat endpoint that were being generated from the load test. And then I can see like basically a distribution graph of how long it took for them to run. So some of those were fairly quick, but most of them were kind of around this 8-9 second mark. So I can see like that's my expected range for the performance. And I can select that in here and I can see the 50th percentile is about 9 seconds. So what I can do is then in application insights, I can drill into one specific request, and it will then show me exactly what happened. So, you know, when it made the API call, you know, what happened in this particular case. And I can see the reason actually it took probably that long is because there were actually several chat requests within that. And the reason is because I had tools. So the initial user request was, is my order delayed? And I can see in the trace that it made a request to the AI model, and then it ran some tools, and then it gave the output of the tools to my next chat response. So actually, the reason why the performance in this case is a lot slower than I would expect is because the way I configured these particular tools to go and fetch the user orders, it's giving the initial request from the user was a pretty short question. And my initial prompt wasn't actually very good. I didn't say to the AI, you can't handle questions about delays in orders. All I said to the AI in my system instructions was, you help users with looking up their orders, but you can't actually answer this question. So what the AI is doing is it's running tools that it finds, and it's going to then do another chat request. And this second one actually took 6 seconds, whereas the original one only took 2. And so it's gone that, and it's then got to stream all that data back to the user. So the reason my app in this case is taking 8.6 seconds is because my initial system prompt was pretty poorly written. And in my case, I should have actually improved that, because we probably could have gone back to the user at the 2-second point and said, you know, actually, we're not able to answer that question. Or we could have, you know, tried to implement a different feature. And because I was really vague in my initial system prompt and said, you're a helpful agent that helps users with orders, but never actually gave the agent enough information to answer the question, then it's kind of just bouncing around for 10 seconds before coming back to the user. If you go back to the other screen, please, Anna. There's a question in the chat, actually. Maybe we can promote that one. Do we have a general cost estimate about how a well-designed AI app should cost, meaning the percent cost of AI's LLMs compute and resources versus applications? Yeah, that's a good. There's a lot to unpack there. My general recommendation is you should consider the cost of AI as being the cost per token. That's kind of how it's measured right now, and that's generally how it's charged. So, you know, the fewer tokens you can use to achieve the same outcome, the better. So in the example I just gave, actually the AI would have consumed quite a lot of tokens just calling tools unnecessarily. And what we're seeing now in particular is that with the introduction of more and more tools and agents into AI workflows, that if they're not well designed, the costs can increase because the AI is running a lot of tools and putting more and more into the context, and you're using more tokens to get to a response. And often the response from the AI could be, "I'm sorry, I can't help with that," because the user asked a question that you haven't implemented. So it does make a huge difference. Tokens are the way that AI is charged for right now. And in terms of the actual compute, I'd say if you're consuming AI as a service, like by the tokens, then that's one consideration. Otherwise, if you're running them on infrastructure and you're looking at the cost of the infrastructure, generally today the big cost is the hardware and then the power, because this infrastructure does use a lot of power. And that's generally because there is just so much calculation in order to generate a single token, like we talked about. But I can't give you a percentage number. So yeah, if you go to the next
The
slide.
answer is it depends.
Yeah, it does, definitely. Great. Yeah, so like I mentioned, you can do a lot in the prompt to reduce the amount of tokens and the length of the answer. And in this example, I've got a comparison where I've asked the same question to two different models. One of them took like a second to answer, and one of them took almost a minute to answer. And the reason is because the second model gave a much longer answer. And I asked it the same question. So the point here is that the model that you pick, and in the right-hand side, I picked a reasoning model to answer a simple Q&A question. And so it's done a lot of consumption of tokens. It's taken a lot of time to get to the answer that I didn't really need to generate all of that information. What I was looking for in this case was what is the capital of Azerbaijan, which could just be a single word, which is Baku, or it could just be a single sentence. But this AI model on the right-hand side actually generated several paragraphs. And what we see in AI models today is that if you don't optimize your initial prompt and you don't set the expectations about the length of the output, and also the format of the output is really important, then you'll just get longer answers. The bigger models today try and achieve better results and better accuracy by giving you longer responses. So if you don't be specific in your initial prompt that you want something that's short and concise, it will tend to a longer answer. Longer answer means it takes longer. It also means it consumes more tokens. So this is something that's a big consideration. The other thing we can look at is also the precision. Generally, if you're consuming AI models as a service, you don't normally get control over the actual precision formats. But within the model itself, the calculations that Stephen talked about earlier, where you've got weights and you need to do matrix multiplications within the model, those numbers, the way that we actually store them and compute them on the processor, is a format. And generally that format is a 32-bit floating point value or a 16-bit floating point value. Now, one of the advancements over the last few years is that we've actually started to compress those formats down. The goal of that is so that a single instruction on the processor can actually do multiple calculations at the same time. So where previously you've got 32 bits used for one number, 32 bits used for another, you want to multiply them together in a 64-bit register, that's one instruction. Now, if you could actually pack more numbers into the same register and multiply them all at the same time, potentially you could do 4 multiplications instead of 1. And the downside of that is that we actually see a reduction in the accuracy. However, the reduction is really not that noticeable in most cases, which is why it's a really compelling technique. So this is something that we call quantization, which basically means that we're looking at reducing the precision format so that we can do more calculations at once. Also, the size of the models is smaller. So generally, you need a lot less memory to operate them. And the compute resources that you need as well is also less. So what we do is we basically we kind of approximate the values, but we reduce the precision in order to fit that number into a fewer number of bits on the processor, and also in the storage of the actual model itself. Another way of thinking about this is like a JPEG compression. Like if you take an image with a really sort of 30 megapixel camera, for example, and you want to compress that image all the way down to like 0.5 megapixel or a megapixel, you'll still recognize what is in the image, but you don't get the same level of detail. And this is the same with quantization. As we reduce the size of the values that we have through lower precision formats, we basically get slightly less accuracy. The performance of the model reduces each time you kind of step down the precision values. Yeah, and we see that basically in this kind of example that yes, we can absolutely increase the throughput, 2x or 3x in some cases, but generally you kind of generally reduce the precision. There are lots of techniques to try and keep the accuracy of the model high, even though it has been quantized. And these techniques are sort of being eagerly researched by lots of different groups at the moment, NVIDIA in particular, because lower precision formats are really well processed on NVIDIA hardware. That there are specialized instructions to deal with these 4-bit values, for example, 8-bit values. So the actual silicon itself is sort of specialized to be able to multiply these types of values together.
Yeah, very well said. And one thing to add on here is that, you know, one of the, like Anthony said, you need to load all of these weights into your GPU memory whenever you are running your model. And if you can quantize those weights from a 32-bit number to a 16-bit number, you only need half as much memory and likely half as many GPUs. So you can just cut your GPU cost in half by quantizing. And if you go from 32-bit to 8-bit, that's a 4-time decrease. So, you know, it's a huge area of cost savings and can simultaneously increase throughput while minimally decreasing accuracy. So on that note, a couple other things about hardware. The hardware that you use to run your model is going to be one of the most important aspects of your performance. Obviously, if you're running on just CPU only, you're going to be maybe getting 0.1 tokens per second. We experimented with that in our last episode. Pamela ran a model locally on her laptop, and I think she was getting like 1 token per 10 seconds. Like it was very slow because of just the hardware isn't made to do that. But if you use hardware that's specialized for that, like an H100 or a B200, though that's where you're able to generate huge amounts of tokens very quickly with very low latency. So every generation, we see massive increases in performance from Ampere to Hopper to now Blackwell. And, you know, we're going to see that trend continue all the way through Vera Rubin and Feynman and even further in the future. So there's lots of performance gains to be had, and we continually see massive increases in performance due to the hardware. So another thing to keep in mind is the sequence length. This kind of fits into what Anthony was talking about with the prompt engineering. If the size of your input to your model, meaning the user prompt, the system prompt, anything gathered from extra context from RAG, all of this data that you're putting in, all of these tokens that you're putting in is considered the input sequence length. And remember that during the prefill process, all of these tokens need to be completely calculated and processed before you can even generate a single new token. So the larger your input sequence length is, generally you see larger latency because you're having to spend more time processing these tokens. Similar for the output sequence length. So the output sequence length is pretty much just the response from your LLM. Of course, if you are using a reasoning model, your output sequence length is going to be much, much larger. So it will take some more time for the model to actually generate its final tokens. So what we see here is a graph showing the correlation between the input sequence length and the time to first token, otherwise called latency. We see a general trend, up and to the right. And unfortunately, this graph cuts off around 650. But if you were to continue this graph into the thousands and the tens of thousands, which is what we see, in modern use cases with, coding and multimodal models, this becomes even more apparent. So if possible, it's better to keep your input sequence length smaller, but of course you don't want to sacrifice the quality of the output. So if you remember, I talked about earlier the batching process. So batching is when the model is processing multiple different prompts at the same time. And this is very helpful to get the most out of your hardware. You're increasing the utilization when you're processing multiple prompts, and also B, to increase the throughput of your model. So this chart shows the batch size correlation with the output tokens per second, aka throughput. And you can see that it really has a sharp increase at first. Then once you get to about 300, it starts to taper off and taper off. And this is happening because the GPU is approaching its max potential, where no matter how large you make your batch size, the GPU just doesn't have the resources to process that number of prompts at the same time. But we do see, around here, we see pretty great increases in performance, in throughput. Now, keep in mind, the batching, like increasing your batching size, isn't just a golden fix. You do see slightly higher latency with once your batch size starts to get too big. But if you're really focused on the throughput, batching is a fantastic technique you can use to increase your throughput. Now, whenever we're talking about the infrastructure and the hardware, Azure and NVIDIA Nemotron really go together hand in hand. So Azure is really focused on providing optimized AI/ML hardware and infrastructure, as well as the entire sort of software ecosystem around it to help you build, number one, build models, and number two, serve them very effectively. So whether you're running on AKS or AML or AI Foundry, Azure has a very optimized stack for this. Now, whenever you're considering models and your suite, that's where NVIDIA Nemotron comes in. So Nemotron Nemotron is not just a family of models. You might be familiar with like the Nemotron Nano or the Nemotron Super. But the Nemotron umbrella extends a lot further than that. The Nemotron umbrella covers not just models, but also the data that goes into them, the libraries that were used to create these models, as well as the research papers behind these models. And what is fantastic about this is that it is 100% open source. So you can go in and see all of the different data sets that were used to train Nemotron models. You can see the libraries that were used. You can see the architecture of these models. And it's a great way to really build your understanding of LLMs, as well as serve very high performance models. So there are, lots of really great techniques to improve the performance of your model. And we covered a lot of them here. Now, here are some really interesting advanced techniques, as I'm calling them, to, really just reach beyond that to the next level of performance with your AI inference. So this is one of my favorite topics. I think it's just the coolest thing in the world. It's called speculative decoding. So, or spec dec for short. With speculative decoding, you're essentially running two models at the same time. And what's happening is you have a target model, which is a larger, smarter, but slower model. Think of like GPT-OSS or Llama 4, any of those, models you're probably familiar with. So that's your target model. And you're serving that like you would usually. But you're also running at the same time a smaller draft model, which is maybe going to be around 5-8 billion parameters. And this is much faster than the target model, and it goes out ahead of the target model, generating tokens that are then passed to the target model to verify. So rather than the target model generating all of the tokens itself, the draft model generates it and passes it to the target model. So if you see the draft model generates brown fox hopped over, but the target model, being more intelligent, says the brown fox jumped over. So it doesn't accept 100% of the tokens generated by the draft model, and that's called the acceptance rate. Is essentially how well these two are performing together. So this is a very, very cool technique you can try. It's all open source. So NVIDIA actually creates a lot of the draft models that peg on to existing target models. So there's an NVIDIA draft model for Llama 4 Maverick, NVIDIA draft model for GPT-OSS. So you can run and try these locally, and it's really cool to see how they work together. And so this is kind of an example of the throughput gains you might expect to see whenever you are using speculative decoding. Now, another sort of advanced technique we can use is called disaggregated inference. So if you remember those two stages of inference I mentioned at the beginning, that was the prefill and the decode. So you can see them right here. The prefill, again, is processing your entire input, generating your KV cache, and generating that first token. And the decode is creating all of the tokens after that. So what you can do with what you're doing with traditional serving is you're running this all on the same GPU. That same GPU is running the prefill and the decode for a single prompt. But with disaggregated serving, you're actually using a particular GPU for the prefill and a different GPU for the decode. And what we see with this is increased throughput, decreased latency using this disaggregated approach. So this is really interesting. There is lots of research, lots of sort of performance gains going on here. And I encourage you to look more into this. One of the big benefits you can get out of this is what's called KV cache aware routing. So you can route based off of your KV cache utilization, or just how much KV cache have you generated? Is your GPU full? You could also use what's called prompt prefix aware routing, which will route a prompt like what is GTC to the correct GPU depending on how good of a match the existing KV cache is in that GPU for this prompt. So this is an incredibly interesting technique, and we see lots of performance gains out of it. If you look at Base 10, they actually wrote a blog about the performance gains that they had using NVIDIA's disaggregated serving framework called NeMo. So you'll see that here. So lots of performance gains that we can get out of NeMo and disaggregated serving. So yeah, that's pretty much what we that's I feel like covers a huge part of the AI inference performance gains world. Lots to sort of research yourself. I encourage you all to go look into these topics, watch some YouTube videos, read some articles, talk to LLMs about it, and try it out for yourself. This QR code will take you to a blog from Microsoft explaining how you can deploy a model from AI Foundry. And it doesn't explain it in the blog, but I encourage you, once you have it up and running, to try out some benchmarking tools and see what kind of performance you can get.
Yeah, thank you so much, everybody, for joining us today. And yeah, thanks, Stephen, for your time and expertise. It's been enlightening, lots of new terms to bring home. So hopefully we've given you some practical application of what you've learned, but also you've learned a bit more about the details of what's really happening under the covers. And I think it's pretty fascinating when you use the AI and you actually appreciate just how much calculation has to go into a single token, and how impressive it is that we can get 700 to 1,000 tokens a second out of a single compute node. So yeah, thank you very much for your time today, and it's been a pleasure to host you all.
Yes, thank you, everyone.
Thank you all for joining, and thanks again to our speakers. This session is a part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. And we'll see you at the next one.